Hi, I'll be going into chapter 7, which is the internal force. Yeah. Okay. Today's objective would be to use the method of section for determining the internal forces of 2D load cases. Yeah. So application. Why do we need to study this topic, and where do we apply it? Yeah. Beams and structural members designed to support loads applied to the perpendicular to their axis. Yeah, like example, let's take an example of this beam that is for the bridge itself. Yeah, so they are often thicker at the supports and at the center of the span. So if you see, how do we know the variation of the thickness here and the thickness here? So there must be a sort of studies that's being done, like internally, what are the forces that exist or that's happening that you need to study. So that's the reason why, like, what's the force here, what's the force here. Based on that is the one that we can actually design the bridge or any structure, where it has to be thicker and where it has to be thinner. Yeah. And so that is the reason for this chapter. Yeah, and also many types of applications. Just giving you one or two examples. So look at these. This is a billboard. Yeah, fixed supports these rectangular billboards. Usually such columns are wider and the thicker at the bottom. Can you see this plan? It's wider and thicker at the bottom compared to above. Yeah, so how did you come into this kind of conclusion? So there must be some sort of study that's being done, right? So that's the reason why we are looking at this chapter. Yeah, and look at this structure. This structure suddenly has this what do you call this support, external support here. So these are the reasons. Okay, now let's look at the internal forces. What are the internal forces? Let's take a beam here. Okay, the design of any structural beam requires finding of the forces acting within the member to make sure the material can resist the load. Yeah, so we have to study internally because we need to know whether the load can be resisted by the beam or not. Okay, so looking at this is actually a roller, so you have one external force. This is a pin, so you have two dy and dx. Yeah, and in this, from the previous chapter, right, there's no any horizontal forces, so automatically dx here becomes 0. That's the reason why they didn't even show by right there is a dx. Yeah, okay. So next, they are actually telling you to study at the section at B. So at B, so when you open and cut at B, so of course the internal forces are exposed. So this is a set of forces. This is a normal force, moment, and shear force. They come in as a package. So yeah, you have to, the moment you expose it, cut this, okay, what happens is that you're exposing all the three forces. So right, likewise, you have another partner, right, from this side. Okay, this is from this side, this is from this side. Okay, and then you have a partner which is from the opposite side, like this part is drawn at here. Okay, the next slide will show you in detail. So this will also have a partner NB, and then this pointing down, so this will be pointing up. This is what you call anti-clockwise, so this will be clockwise. So they are partners. So when you join them together, they cancel off. Okay, let's look at the next slide. Okay, so what are internal forces? They are made of normal forces, and then they are made of shear forces. That's a V, the shear force, and then we have normal force, the N, and then we have the bending force, the M. Okay, so when you cut open, because the internal forces, when you join them, you don't see because they cancel off each other, right? So that's why you see this V down, V up, MB to the right, MB to the left, and then we have the what do you call this? The moment. Yeah, one is clockwise, one is anti-clockwise. When you join them, you don't see any of them. But what about this P1 and P2? These are all external forces. Yeah, these are all external forces. Yeah, they don't come in the category of internal forces. AY, AX, moment are all external forces. Yeah, they're all external forces. So they don't come in a category of, these are all external forces. Means when you join this together also, you will still see the external force because they're coming from outside. Yeah, okay, so let's move on to the next one. Steps in determining the internal forces. take an imaginary cut, yeah, at the place where you need to determine the inner force. Mostly the question will actually tell you where to cut. Okay, if necessary, determine any support reaction of the joint forces by drawing the free body diagram. So first, you have to solve the entire free body diagram. Entire. Once you have done, then you go to the respective place. So if let's say the thing that to cut at B, so you only expose B and you show. But the external forces here, in the whole free body diagram, you have actually calculated. So you just have to repeat here. Okay. Then you apply the EE equilibrium equations, yeah, to solve the internal and external load. Okay, let's look through an example from the textbook. Yeah, you know that I always skip the example in these in the lecture note because it's a bit easy. You can just go through. I'm going to take a tougher one and I'm going to show you the calculations. Yeah. Okay, let's look at this structure first. Okay, so we have what? Determine the normal shear force and bending moment acting to the left of point B. So just left to the point B and just right. And then they also want point C. Okay, so what we have here? Okay, we have B just before, just after, and to the right of point B, point C. So you see, when I enlarge this rod, it's going to look something like this. B and C has a gap actually. So they want first one here, second one at point B, and the next one to the right of point C, which means taking into account of point B and point C. That is the what do you call the magnification? Yeah. Okay, if you look here, this is a roller, this is a pin. Okay, like what I've told you, one force here, one force here, one force here. First step is to draw to solve the whole free body diagram. This is step one. It's compulsory step. Okay. Whether you want to take on the left side or the right side, you don't bother, but you need to do the whole free body diagram and solve it. So from here, we know the AY is actually 5 kilonewton. Okay. Now this working, they didn't solve for dy and dx. You can actually continue to solve your dy and dx. I will let you know why it's important to solve all dy and dx. So once you have got the whole free body diagram, next, the first question is what? They are asking you just before point B. So which means you need to draw just before point B. So just before point B means just before the 6 kilonewton. So this would be the first segment that you need to draw just before. Okay. So if you look at this segment, you have a 5 and you have, of course, you have 3. Then we have all the internal forces that comes as a package. So this is a standard line that you need to write. Yeah, this is a standard line. Okay. Your marks come for this, and this. This is a standard line. I repeat, this is a standard line. This has got marks in the exam. Yeah, even though we know NB is 0, you need to show this line because this line carries 1 mark or probably 2 marks depending on the question itself. Okay, next step is to solve for your Fy. So in this case, what do you have? You have your 5 and you have your VB. So you have your 5 and VB pointing down, which means when you solve it, VB becomes 5 kilonewton. Okay, settle. The next part is to solve for the moment. Okay, so MB is the summation of moment of M at MB is 0. So because you are taking moment at B, so what happened? 3 minus 5 multiply 3. 5 multiply 3. And then you have an existing moment which is MB. So how did you get the value as negative? Because this is actually going around clockwise, around point B. So that's the reason why this is negative. When you solve it, you get your MB as 15 kilonewton. Okay. So I hope you can understand. So the next part would be to solve for segment AC. So what is segment AC? Segment AC is the second part of the question, which is what? Okay, let me just go there. Okay, moment acting just to the left of point B and just to the right of point C. So just now you did what? You did this part, right? Just before the B. And the next one, they are actually asking just to the right of point C. Just to the right of point C, which means they want this whole segment. Okay, so to the right of C means it will include the 6 kilonewton. Okay, let's move on. So this will be the free body diagram for segment AC, the second part. we have the 5, the existing, and of course we have the 6, which just came in after the C, right? Because you're taking at C, and this comes as a package. Can you see that? This is again repeated, like as if it's a package. Yeah, fx equals 0, fy equals 0, and mc equals to 0. Okay, repeating the whole thing again. nc equals to 0. Understood. Okay, next we have vc. So what do we have here? 5 pointing up, 6 pointing down, 5 pointing up positive, 6 pointing down negative, and we have the vc, which is negative. So conclusion, vc will be negative 1 kilonewton. Now what does it mean by vc equals to negative 1 kilonewton? In this free body diagram, we have pointed vc as down, right? Okay, if you calculate and you get a negative value, which means the direction that they have taken for vc is actually wrong. It has to be the opposite side. So small matter, it's okay. You don't need to turn it around, but you just have to keep it as vc equals to negative 1 kilonewton. This answer is actually acceptable. Okay, next we do for your mc. Where is the mc? mc is here. So we have what? I'm going to erase all this, yeah, because so much of scribbling. Okay, let's look at a clean sheet now. Okay, so now we have mc. Okay, mc is at anti-clockwise, so that's why it is positive, and we are taking moment at C, at point C. So we have 5 multiplied 3. Okay, 5 multiplies 3, and 6 is at C. So 6 multiply 0. That's the reason why there's nothing here. Okay, so we get MC as 15 kilonewton. So we have done this part of the question. So this is a bit straightforward. Now I'm going to go to the second part, which can be a bit complicated. It's not too complicated, but you can just pay attention. It all will be okay. Okay, now let's look at this question here. This is a distributed load. Okay, and they are actually asking to determine the normal force, shear force, and bending moment at point C. So where is C? C is right in the middle. Okay, so let's look at how to actually know what is, you see at the end here we know it's 1200, no problem. But at C, how much is this? Because we need to draw, right? Yeah, we need to draw. So what happens here? Okay, let's look at a similar triangle concept. Okay, the whole big triangle with a length of 3 meters, the end here is 1200. You get it or not? Okay, now we are taking a ratio. So now I'm cutting at point C, which is 1.5, which means it's just half of it. So 1.5 to 3. So how much is this? This will automatically be 600, right? So it's a ratio. So the calculation for the ratio is actually given here. Yeah, if you see the big triangle ratio to the small triangle. So that's how you get your 600. Okay, so drawing the free body diagram at point C. Yeah, at point C. So what do you have? We have all these forces exposed, NC, VC, and the MC. Yeah, all the forces that's exposed. So what is the VC value here? The VC value here is the value that we just calculated, which is 600. Okay, now since this is an evenly distributed loading, for a triangle, we know triangle is centered at 1/3, right? 1/3, right? Yeah, the distance is 1/3. So this will be 1/3, this will be 2/3 of the whole triangle. So this will be 2/3 of the whole triangle. So what is the value here? It will be half times base times height. Okay, so the distributed loading will be represented as half times base times height. Half times base times height. So where will it be? It will be right here at the distance of 1/3. Okay, so that is the segment. So that would be the calculation for point C. So let's look at point C. Once again, this comes as a package. You like it or not, you have to write it. Yeah, NC is 0.1. This is the first point. Okay, the next one would be Fy equals to 0, where we have VC minus, okay, half times base times height, which is the force that's going down here. Can you see VC is going up? This force is coming down. So what is this force? Half times base times height. So VC will be 450. Okay, so the next part would be to solve for the moment. Okay, let's look at to solve for the moment. So what we have MC, existing MC, and then we have this force, right? This force, isn't it? which is half times base times height. And what is the distance to C? 0.5. So half times base times height multiply with 0.5. And the value is negative because it's going around clockwise around point C. Okay, so that's the reason why MC is negative 2.25. So that's it for chapters 7.1. We will continue in the next lesson.